If we are solving an Euler Cauchy equation and we have a complex roots in the equations we mentioned previously, then we will discuss now how we're gonna handle that kind of problem. Now, how to identify that you have a complex roots case. In that case, the resulting m1 or m2 roots of that equation will be looking like alpha plus or minus I multiplied by beta. Okay, in that case, what you will do, firstly, you will assume the t to equal ln x. Then, your general solution in terms of t will equal c1 e to the power of m1 cosine the value of beta multiplied by t plus c2 e to the power of m1 sine the value of beta multiplied by t. And since the t is assumed to equal ln of x, in this case the y of x will equal c1 e e to the power of m1 multiplied by t and multiplied by t in here as well. Apologize for that. So the y of x equals c1 e to the power of m1 multiplied by ln of x multiplied by cosine beta the ln of x plus c2 multiplied by e to the power of m1 ln of x multiplied by sine the beta multiplied by ln of x. So these two forms will be coming useful while solving an Euler Cauchy equation with the complex roots. Now let's take an example to apply what we learned. You have an equation of x squared multiplied by y double prime plus 3x y prime plus 10 multiplied by y equals 0, and it's telling you to find the general solution of this equation. Now, as we said, you will assume the t to equal ln of x, then you apply the general form for the y of t. General form for the y of t will be able to apply it after you find the roots for the second form of the equation. So let's use this form first. So we have m squared plus m multiplied by 3 minus 1 plus 10 equals 0, and this will give you the roots for this equation will be so if you try to solve it, you will have minus 1 plus or minus 3 multiplied by I. So this is your alpha for which is common between M1 and M2, So we can say this one is can be compensated with the value of alpha, which will be the same basically. So this is your alpha, and this is the value for beta. Now the y of d equals c1 e to the power of alpha, or m1, or the first real part of m1, which is -1 multiplied by t, cosine the value of beta 3 multiplied by t, plus c2 e to the power of minus t sine 3t. Now the final solution that we're looking for is the y with reference to x. If we compensate the t with ln of x, we'll get c1 multiplied by e to the power of minus ln of x cosine 3 multiplied by ln of x plus c2 multiplied by e to the power of minus ln of x multiplied by the sine of 3 multiplied by ln of x. And this is the final solution for the Euler Cauchy equation with complex roots. Now, what if you have an Euler Cauchy equation, and after you apply the steps that we discussed briefly before, then you find your roots to be in case 3, which is repeated roots. So you're having m1 equals to m2. Now in that case, you wanna say that the value of y1 equals x to the power of m1, and the value of y2 will equal u multiplied by the value of y1, and you define u to equal the integration of v dx, and the v, which is the same v in here, equals 1 divided by y1 squared multiplied by e minus the integration of p of x dx. So it's like now you're having a regular second order differential equation with an initial condition of y1 as known. We discussed that previously. We're just following the same steps basically, and eventually your general solution will look like this. It will be like c1 multiplied by y1 that we found earlier plus c2 multiplied by y2. We are not going to solve an example on that because we already solved many examples on a similar topic previously that you can go back for it and watch it. So this is the final solution, the way it looks like if you have repeated roots for an Euler Cauchy equation.